Understanding inventory dynamics in supply chain analytics. In this lesson, we will learn how to analyze and understand inventory behaviors using real-world supply chain datasets. Inventory management is crucial for avoiding stockouts, reducing costs, and maintaining high service levels in supply chains. You will learn to transform raw transaction data into actionable insights about stock levels, demand variability, and replenishment needs. We will practice common analytics patterns using realistic retail and manufacturing data. Running the cell now. We import pandas for working with tabular supply chain data. We import NumPy for numerical operations that help with inventory analysis. We import the warnings module to suppress unnecessary warnings. We turn off warnings to keep output clean while focusing on business questions. Running the cell now. Core data concepts: transactions, inventory, demand, orders. Operational datasets in supply chain analytics include transactions, inventory snapshots, demand forecasts, and order histories. These datasets are often structured as transaction logs, time series, or event-based records. Beginners often misinterpret date columns, confuse order versus delivery events, or neglect units of measure. Accurate inventory calculations depend on understanding how movements in and out of stock are recorded. Running the cell now. The business problem: we need raw sales and movement data to analyze inventory change over time. We load a real UK retail transactions dataset from the UCI machine learning repository. We use the year 2010 to 2011 data to get actual records of what was sold and when. We convert the invoice date to date time to make calculating stock flows possible. We print the dataset dimensions to see how many transactions we have. We preview the first 3 transactions to confirm the dataset structure. Running the cell now. This output shows the loaded dataset containing over 540,000 transaction records, each representing a stock movement linked to an invoice. Notice the key columns: invoice date as a date time for event timing, quantity indicating movement in out of inventory, and stock code with product details, critical for tracking supply chain events accurately. Understanding this structure sets the foundation for analyzing inventory changes and demand patterns over time in supply chain analytics. Practice: what columns in this retail data are critical for calculating inventory positions? Try listing them before proceeding. Let us check the available columns so we can identify demand and inventory-relevant fields. We display all column names in the data frame to find those related to product, quantity, dates, and inventory. Running the cell now. This output lists all the column names in our transaction dataset, helping us understand the data structure before any analysis. Notice the key fields like invoice date for timing, quantity for movement in stock, and stock code or identifying products. These are crucial for tracking orders and inventory changes accurately. Recognizing these columns ensures we correctly interpret dates and quantities to avoid common beginner mistakes. Many inventory projects begin by selecting just key columns: product identifier, description, quantity, and date, time. We preview the main columns needed to calculate inventory flow for each product over time. Running the cell now. This snippet shows the first 5 transaction records, highlighting key columns like stock code, description, quantity, and invoice date. Notice that each row represents an order event with positive quantity values, all occurring on the same date and time, which is critical for correctly tracking inventory inflows. This output underscores the importance of understanding transaction logs as the foundation for accurate inventory and demand analysis. Operations teams want to know how many different products, SKUs, they manage. We count the total number of unique stock codes to estimate the product assortment being tracked. Running the cell now. Here, the code counts the number of unique stock keeping units, SKUs, in the dataset, showing there are 4,070 distinct items tracked. This highlights the dataset's complexity and reinforces the importance of correctly identifying and handling individual products when analyzing inventory and transactions. Understanding SKU uniqueness is crucial for accurate demand and stock movement calculations. We want to see demand for each product by day. This helps us map out how inventory is consumed over time. We group transactions by product and date, then sum up the quantity for each group to compute daily product demand. We print the top days for some products to review if the grouping worked. Running the cell now. This output shows the daily total demand for each product, stock code, by summing quantities sold per date, collapsing transaction-level details into a clear time series format. Notice the quantity column reflects net sales on each day, which is crucial for accurate inventory and demand analysis by highlighting daily consumption patterns rather than individual order lines. This step helps prevent common errors like mixing multiple transactions per day or misreading timestamp granularity in supply chain data. Let us focus on one SKU to visualize inventory movements and identify potential issues like stockouts. We extract the stock code of the first product in our aggregated demand data. We filter for that SKU to get its daily demand history. We set the invoice date as the index and sort it so inventory calculations are possible. We print all entries for that SKU to inspect fluctuations over time. Running the cell now. Here we isolate the daily demand for a single SKU, stock code 10002, indexed by invoice date and sorted chronologically. Notice how demand varies day to day with some spikes and gaps, highlighting the importance of correctly interpreting date sequences and quantities in transaction logs. This clear time series view is crucial for accurately forecasting inventory needs and understanding purchase patterns over time. Visualizing demand signals helps identify periods of unusual consumption or likely risk of running out. We import matplotlib for basic visualization. We set the figure size to make our plot readable. We plot the quantity sold for this SKU using circles for each day. We add a title with the SKU number to make it clear which product this is. We label the time and quantity axes for business clarity. We adjust the layout and display the chart. Running the cell now. This plot visualizes the daily demand for a specific SKU, showing quantity sold over time as discrete points. Notice the date-based x-axis representing the transaction timeline and fluctuations in demand captured by the markers, which reflects typical sales variability. Understanding this trend is key for accurately forecasting inventory needs and aligning orders with actual demand patterns. Try picking a SKU with more volatile demand and plotting its time series to see how inventory could be affected. Example: calculating simple inventory position. The inventory position for a product is the on-hand stock after accounting for all inflows and outflows up to a given date. We can simulate inventory depletion by using daily sales as product outflows. Without replenishments, the inventory position only falls. Running the cell now. We simulate starting with 300 units of this SKU in stock and adjust for daily sales to track remaining inventory. We set the initial stock level for the SKU to 300 units. We subtract the running total of quantity sold from the initial stock to calculate the ending position each day. We print out the daily demand and resulting stock levels. Running the cell now. This output shows how the inventory position decreases over time as cumulative sales quantity reduce the initial stock of 300 units. Notice the gradual decline in inventory_position, eventually going negative, which highlights the demand exceeded available stock without replenishment. This confirms the concept that inventory position tracks on-hand stock after accounting for all sales up to each date. Visualizing inventory positions clearly highlights when a product will be out of stock if we do not replenish. We plot the inventory position over time for this SKU. We use orange squares to show how stock changes each day. We add a red dashed line at 0, marking the moment of stockout. We label the axes and add a legend for clarity. We show the inventory chart to help forecast risks. Running the cell now. This plot shows the inventory position for a specific SKU over time, highlighting how stock levels steadily decline due to daily sales without any replenishment. Notice the inventory starts positive and trends downward, eventually approaching the red stockout line at 0, which marks when the product runs out of stock. This visualization reinforces the concept that without inflows, inventory only diminishes. Think, what would happen if sales spiked for this SKU? Predict the day it runs out if replenishment stay at 0. Example, filling in missing dates in inventory series. Sales records may not appear on every day, so we must fill missing dates to produce a continuous inventory time series. Missing dates can lead to underestimating how long an item has been out of stock. Running the cell now. An operations analyst should build a complete timeline even when some days show no sales, so we do not miss latent stockouts. We create a daily sequence from the first to the last day in the SKU record. We re-index original demand data to include all dates, replacing missing demand with 0. We recalculate inventory position, ensuring there are no gaps in the day-by-day progression. We print the first 10 days to confirm missing days now appear. Running the cell now. This output shows how we filled in missing dates with 0 sales to create a continuous daily record for the SKU. Notice the row for the 4th of December, 2010, where quantity is 0, ensuring no gap in the time series. This complete series allows accurate tracking of inventory position, reflecting cumulative sales and preventing underestimation of stock availability over time. Business leaders care about how long a product stays out of stock. We calculate the number of days when inventory position is 0 or less, indicating a stockout. We print the total number of stockout days for this SKU. Running the cell now. This output shows there are 113 days where the inventory position is 0 or negative, indicating stockouts. Noticing this count helps us understand how often an item was unavailable, reinforcing why filling in missing dates is crucial to accurately track inventory shortages over time. Practice, try rerunning this analysis with a different starting stock. How does that change the number of stockout days? Subscribe to our YouTube channel for more supply chain analytics walkthroughs. Intermediate example, calculating rolling average demand. Smoother demand estimates help plan reorder points in volatile environments. Rolling averages filter out random spikes and dips. Running the cell now. In uncertain demand environments, rolling averages are used to set inventory thresholds. We create a new column with the past 7 days rolling mean of sales quantity. We print the quantity and corresponding rolling average to compare raw and smooth demand signals for the first 10 days. Running the cell now. This output shows the original daily demand quantity alongside the 7-day rolling average demand, rolling_demand_7D. Notice how the rolling average smooths out volatile daily fluctuations by averaging the current and previous day's quantities, providing a steadier trend that better informs reorder planning. Early on, with fewer than 7 days of data, the rolling average still calculates using available days, helping maintain a consistent estimate from the start. Visualizing both raw and smooth demand helps reveal underlying consumption trends. We plot both the actual daily demand and the rolling 7-day average for a single SKU. The rolling mean line is shown in bold for better visibility. We show the plot to see how smoothing stabilizes noisy sales data. Running the cell now. This plot compares the daily actual demand, dots and light line, against the 7-day rolling average, thicker black line, highlighting how the rolling average smooths out the day-to-day volatility. Notice how sharp spikes and drops in the actual demand are softened in the rolling average curve, providing a more stable trend useful for planning reorder points. This demonstrates the power of rolling averages in filtering noise to make demand forecasting more reliable. Replenishment policies often use multiples of average demand to set reorder points for safety stock. We estimate a reorder or replenishment point as 3 times the average rolling 7-day demand. This gives a rule of thumb value for when to restock. Running the cell now. The output suggests a reorder point of 22 units, calculated as 3 times the average 7-day rolling demand. This highlights how the rolling average smooths daily fluctuations to provide a more stable demand estimate, helping set a practical and responsive replenishment level. Using this approach ensures that reorder points are aligned with consistent trends rather than volatile daily sales. Now let us examine a manufacturing operations dataset from OpenML to practice inventory analysis on a different industry. We import OpenML to fetch public real manufacturing datasets. We download a real OpenML dataset on manufacturing operations, often used for production planning. We unpack data features and, if present, a target variable. If present, we join feature table and target so downstream analytics will work regardless of dataset structure. We print the dataset size to verify we have many records. We show the first 3 rows to get a feel for this operational format. Running the cell now. This output shows the shape and first 3 rows of the manufacturing dataset, confirming it has 32,769 rows and 10 columns with encoded categorical features. Noticing the dimensions and sample data structure here ensures we understand the dataset size and variables before calculating rolling averages for smoother demand estimates. This step sets the foundation for applying rolling functions to filter out volatility in demand patterns. Intermediate example: aggregating inventory by line or location. Manufacturers often want to track inventory use by production line, workstation, or location. Grouping and aggregation are key analytics building blocks. Running the cell now. In manufacturing, analysts often group usage or demand by the line, area, or plant to find bottlenecks. We check if our manufacturing data has a line and quantity_used field to sum usage by line. If present, we aggregate and print summary inventory outflows per production line. If missing, we print a reminder that grouping is a standard analysis step. Running the cell now. This output indicates that the data frame lacks the necessary line and/or quantity_used columns to perform the intended aggregation. In this lesson on grouping and summing inventory by production line, it's important to ensure your data contains the correct columns before applying Group B operations. This check prevents errors and highlights the need for proper data preparation in analytics workflows. Practice: try customizing the grouping to a column relevant to your supply chain or plant. Analysts estimate safety stock based on demand variability to buffer against uncertainty. We calculate estimated safety stock as 2 times the standard deviation of daily sales for our SKU. This helps manage demand spikes or supply delays. Running the cell now. This output shows the calculated safety stock level, derived as twice the standard deviation of daily inventory quantities, which here is about 46 units. Notice how this measure captures the typical variability in stock, helping manufacturers maintain buffer inventory by line or location. This reinforces the lesson's focus on using aggregation, standard deviation, to inform practical inventory management decisions. Error handling example: missing or malformed data. Inventory analyses can break if sales or supply logs have missing values, unexpected negative numbers, or date gaps. Always validate and clean operational data before analytics. Running the cell now. Real data sometimes has missing quantities, which will break calculations if not handled. We simulate a missing value in the quantity column. We count the number of missing values to highlight the issue. We print how many sales records are missing quantities. Running the cell now. This output shows that one missing value has been intentionally introduced and correctly detected in the quantities column, highlighting the importance of identifying gaps in your data. Noticing even a single NaN is crucial because missing or malformed entries can disrupt inventory analyses and lead to inaccurate insights. This step reinforces the lesson's focus on validating data before proceeding with any analytics. Business case: for many retail settings, missing quantities can be safely replaced with zero demand. We replace missing quantity values in the raw retail data with zeros. This prevents errors and ensures inventory decrements are realistic. Running the cell now. This output confirms that missing values in the quantity column have been replaced with zero, preventing errors in later calculations. In this lesson on error handling, it highlights how filling missing data ensures that inventory analyses won't break due to NANs, maintaining data integrity for accurate insights. Missing or invalid dates are dangerous for inventory time series analysis. We count the number of missing invoice date values that would cause timeline errors. We print how many records might break inventory tracking. Running the cell now. This output shows that there are no missing values in the invoice date column, indicating the date data is complete and clean. In the context of error handling, this means our inventory analysis won't be disrupted by missing dates, confirming the first step of validating data quality before proceeding. Negative quantities may signal returns instead of sales and should be carefully classified. We count the number of negative entries in the quantity field. We print this to alert the operations team to potential returns or data errors. Running the cell now. This output shows there are 10,624 negative values in the quantity column, indicating many data errors in sales or supply logs. Identifying these invalid entries is crucial before running any inventory analysis, as they can distort results or cause failures. This highlights the lessons point: always validate and clean your data to ensure accurate and reliable insights. Advanced example: join inventory movements to supplier performance. For robust supply chain visibility, analysts often join stock records to supplier reliability metrics. This allows us to link inventory shortages to procurement and supplier risks directly. Running the cell now. We fetch a supplier performance dataset so we can later enrich inventory reports with supplier risk data. We use OpenML to download supply chain supplier performance data. This dataset covers procurement and logistics KPIs for real suppliers. We print its size and show the first few records. Running the cell now. This output shows the supplier dataset loaded with 9,228 rows and 13 columns, providing detailed employee and payroll information relevant to supplier organizations. Notice key columns like salary, department, and hire date, which help link workforce data to inventory movements. The intent here is to prepare and explore supplier-side data before joining it with inventory records to analyze the impact of supplier performance on stock levels. In a real supply chain, you want to connect inventory flows with supply risk by linking on stock code or item identifiers. We check if the supplier data has stock code and merge inventory records with supplier metrics. If columns are missing, we inform the learner but reinforce the join pattern. We show an example of the enriched data frame. Running the cell now. The output indicates that the join could not occur because the supplier dataset lacks the stock code column, which is essential for linking inventory movements to supplier performance. This highlights a key data preparation step, ensuring join keys exist in both datasets for a successful merge. Without this, we cannot enrich stock records with supplier reliability metrics, limiting our supply chain insights. Advanced example: predicting stockouts with lead time simulation. Predictive inventory analytics simulate when an item will run out, plus the earliest time replenishment is feasible. We can do a basic lead time simulation using expected delivery delays. Running the cell now. Supply managers want to know the earliest date to reorder before a projected stockout, considering supplier lead time. We assume the supplier takes 7 days, lead time, to deliver replenishments. We find the first date in our SKU series when stockout occurs. We set the current or first day as today. If stock runs out, we subtract lead time from the projected runout to get a recommended reorder date. If not, we print that inventory is currently sufficient. Running the cell now. This output shows the calculated reorder date, which is 7 days before the projected stockout day when inventory hits 0 or below. The key takeaway is how the code uses inventory position and lead time to predict the optimal reorder timing, ensuring replenishment arrives before stock runs out. This reinforces the lesson's goal of applying lead time simulations to prevent stockouts through proactive ordering. Best practices: inventory aggregation, time series grouping, KPI calculation. Always aggregate inventory by business-relevant time intervals, day, week, or period. Grouping by SKU, category, or location exposes blind spots in stock coverage. Calculate KPIs such as stockout duration, replenishment delay, and service level to guide operational improvements. Running the cell now. Service level is a critical operations KPI. It measures the % of time inventory is available. We mark each day that our SKU is stocked out with a Boolean flag. We calculate service level as 1 minus the % of time out of stock. We print the calculated service level as a percentage. Running the cell now. This output shows the calculated service level, which is just 24.16%, meaning the inventory was out of stock over 75% of the time. The code identified stockouts by checking when inventory position is 0 or below, then averaged these instances to quantify service reliability. This KPI highlights a critical blind spot in stock coverage, emphasizing the need for better aggregation and inventory management at the SKU level. Exporting inventory calculations allows other stakeholders to review and take action quickly. We save the daily inventory positions as a CSV file for further use by planners and supervisors. This lets business teams cross-check results in Excel or downstream systems. We print confirmation of the file location. Running the cell now. This output confirms that the daily inventory positions have been successfully exported to a CSV file, enabling further analysis. By saving the data with a clear date index, the code supports best practices in aggregating inventory over time, which is essential for tracking trends and calculating KPIs like stockout duration or service levels throughout the time series. Now opening the exported CSV so you can review daily inventory levels and stockout trends. Mini project, from raw retail data to final inventory KPI. You now understand how to transform transaction logs into business-ready inventory insights. As an exercise, load any SKU, fill in missing days, simulate running out, and export the results. Use the patterns in this notebook to analyze your organization's products or a new dataset. Running the cell now. For more practice problems and supply chain analytics tips, follow our free YouTube tutorials.